medicines, the commercialization of medicines. And when I'm not doing this type of work, I'm sometimes thinking about statistics, epidemiology, and its intersection with population health and philosophy. Today, we're going to be looking at inference. What we're going to be looking at when we're going to be talking about what inference means or statistical inference. But what underlies this is the why and the how of research. Very quickly, I'm going to say that this class, the way I teach is very interactive. I prefer my courses to be interactive. And so I will ask questions and feel free to unmute yourselves to answer. What I tend to do is I ask people to volunteer. So if there's a set of questions that I want answered to make a teaching point or put a teaching point across, I would ask people to volunteer. If you're excited about volunteering, unmute yourself. But if there's noise in your background, then you don't have to volunteer. Okay. At this point, I'm going to ask Ore, are these sessions recorded? And do you want to start recording if that is so?
Yes, we are recording at the moment.
Oh, excellent. Okay. And then tell me if there's a noise in the background, I can move to a quieter place. Okay. So we're talking about inference. And you don't have to understand this technically. You can understand it in everyday language. And an inference, what do you infer from what has happened? You see, someone has crunched numbers, someone has had a discussion, and someone would say, what can you infer from what is going on? What can you conclude in statistics or in epidemiology? What can you infer statistically? And that means what can you conclude with a high level of certainty? And I'm going to talk about certainty in maybe the next slide. So the outline, scientific reasoning, samples and sampling, hypothesis, p-values, confidence intervals, and significance. These are the things that you need to go through before you can statistically infer. At this point, okay, now let's move on and let's talk about scientific reasoning. Yes, I was going to ask a question. If someone's kind enough to unmute themselves, go ahead and do it. Here's the question: why do we do research? And does anyone want to answer that question? Let's see, I'm going to volunteer Jerry Mbaka. Jerry, why do you think we do research?
Okay, so we do research to either find synthesize new knowledge,
okay,
or validate existing ones.
I like that. I like that too. So we're trying to discover things, right? And or you want to validate. Does anyone have another? Someone says for decision making. I like that. I see that in the chat. Does anyone else want to talk about why we do research?
I'll say for planning as well.
For planning,
inform planning and forecasting as well.
Okay, tell us a little about that, Ada.
Yeah, so with the output from research, you're able to plan. For example, if you research maybe number of consumables required for maybe an outbreak response,
okay,
you're able to get an outcome. You can use that to plan for maybe similar outbreaks if they happen again or in another location.
I like that. Okay, so that's like monitoring, evaluation, response planning. Okay, so someone said to discover new things, to validate. I see establish scientific facts about a particular population. Excellent, excellent. So I'm going to tell you, so all of this is are true and all of this is correct, I'm going to tell you that epidemiology and statistics is an outshoot of philosophy, right? People were concerned about the truth, you see, and Jumoke Abdul Wahab says it there. We want to establish scientific facts. Sometimes you want to just establish what is the truth, you know, whether it's scientific or not. And so over time, people have said, let us develop a method that is very solid or solid enough that we can all agree on, and use this method to establish quote unquote scientific facts. So you're correct. I like what Yusuf said. Yusuf said it's for decision making, and that's the approach I take for research. And I think that all of us have said the same thing. If you have established your scientific facts, if you have discovered something new, then what are you using that data for? It's for decision making, right? And so when you think about research, you want to think about insights and implications. So for example, someone might be interested in how tall are the men in Lagos on average. You say the men in Lagos on average are 5'8", 5'7". That's your insight. What is the so what? And the reason I've tried to make this point is so that when you go into the world to do research, you're not just doing research to discover things that you're not using. There has to be a so what. Okay. Let's go through this slide real quickly, so you can see, and feel free to jump in and ask a question if you want. So when we do research, you know, people say that there is deductive and there's inductive type of research. And in inductive research, what you do is you look at data and you predict what the data, or you make a conclusion based on the patterns you're seeing in the data. And in deductive reasoning, what we do is we start from an established truth, and then we go down to reach a conclusion. I don't want to talk about deductive because the work that we do when we use the scientific methods are mostly inductive. But you remember when I said that this came from philosophy? And then they established a methodology. I'm going to say this, that it is only a tool. It is not a surefire way to establish truth all the time. And I'll tell you a funny story. So just think about this, right? Imagine you're a chicken. That's funny. Imagine you're a chicken and someone buys you and takes you home on the 12th day of December, right? And every day at 7 a.m., they come and they give you the best food possible. And they do that day 1, day 2, day 3, day 4, day 5. If you as a chicken are also a scientist, inductively, you're going to reach the conclusion that every day at 7 a.m., someone is going to give you really, really good food. That's the idea of inductive reasoning or the scientific method. You look at the data, you look at the pattern, and then you predict. And Ada said it correctly, you can forecast. But stay with me, you're a chicken. Every day from the 12th of December when they take you home, they're giving you the best food possible. On the 13th day, you sit down and you're expecting your food, but that is Christmas morning. And what happens? Instead of getting food, you get slaughtered, right? So this is one example where even though we have the scientific method, inductive reasoning, established, it is not the only way to determine truth. That is one failing of the method, right? However, it is the best. It is not perfect, but it is the best. So looking at this slide, when you want to do research, there are different ways that you can capture the data that you work on. You can either describe and you say, the men in Lagos on average are 5 feet, 8 inches. But you can also infer, you can say that from our sample, we found that men are 5 feet, men in Lagos are 5'8", And so statistically, we can infer that men in Lagos are shorter than the men in Stockholm, Sweden. Perhaps because the men in Stockholm, Sweden have an established average weight of 6'2". That's an inference, right? And then I think it was Ada that talked about prediction. You can talk about prediction if you're a chicken and then you're fed for the first 5 days, December 12th to 17th. You predict that you're going to be fed the next 5 days and the next 5 days after that. But like I said, sometimes that does not work. Okay, I don't know if you found that funny, but I want you to hold on to that because that is one fading of the scientific method that you need to know. Okay, let's push. One of the first things that you need to do, oh, I need to say this. So in this class, we're not going to be doing technical work. I'm just going to be teaching you the principles around conducting scientific or using the scientific method to reach inferencing or to reach conclusions. Remember, we're starting with insight and implications. Okay, so the first thing you want to do, and maybe I should ask someone a question here. I would pick Ada because first time we picked a guy. Ada, tell me, suppose you wanted to understand whether a particular style of teaching was important, was better than another style of teaching. What would you do? How would you go about it?
I think I'll do like a survey
You do a survey?
With the students to understand the teaching styles they prefer, and from the survey results I'll be able to know which teaching is preferable.
Yeah, you're on the right track. Have you guys ever seen that video where the father calls his two children and says, "Give me instructions on how to make peanut butter and jam sandwich"? And then the children are like, "Take the bread," and he's like, "Take the bread? What do you mean?" Who has seen the video? Has anyone seen the video? Give us a thumbs up. Well, if you've not seen the video, you should look for it. Father teaching children how to. Okay, someone has seen it. Godwin has seen it. So Ada, let me play the role of that father in the video. So you're just going to go into the street and survey anyone who's a student. Tell me more.
So I would expect that maybe the teaching is in a setting,
Okay.
maybe a school setting.
Okay,
and
so
maybe
the
a particular
teaching would have been done in a school. Okay, good.
Yeah, and in the class.
Okay, in
I
one
believe,
class.
yeah, and I also think the students in the class, obviously, they always interact with different teachers taking different subjects.
Okay, so that's your belief. Okay.
Or assumption.
That's your assumption. Okay.
Yeah. So
okay.
To understand the preferred teaching style, I would pick a student from each role in the class. So maybe there are 10 roles. I could just pick a student from each of the role in the classroom and then collect their observations or their data to understand their preferred teaching style.
Okay. So I like that, right? But you can see that it's a little incomplete, and maybe Godwin. So Godwin, feel free to unmute yourself and tell me, take it from where Ada stopped. Tell me how you would conduct, given that you've seen that video, so you might know where I'm going to with this. Godwin Ojonimi, I believe that was the person who gave the
tell me. Yeah, hi, Ebuwa. Yes, so I might have forgotten most of the parts of the video, but however, I'll make an attempt.
Let's go. So don't tell me about the video. Tell me about how you will.
Yeah, I'll answer the question. Yeah.
Let's go.
So I will basically come with the assumption that there are teaching styles, and these teaching styles are different. And there are standards for evaluating each style, or for conducting, or principles for implementing each of these teaching styles. And what I would also do, what I'll do would also be to probably recruit teachers or gather teachers who know how to apply each of these principles. Maybe the teachers who predominantly use either of the principles. Let's say there are two teaching styles.
I like
and
that.
Then I would now have them. My own way will be to try to do something like a quasi experiment, actually, and and have them, and then also, of course, look for people who would be students. It could be a category like, let's assume that these are secondary school students and it's how to teach a particular subject. I'm assuming that let's say this mathematics, and then we're picking people from.
Let me combine what you and Ada have said. And before that, let me tell you the reason why I've asked these questions, right?
Okay.
We don't want you to know the methods without knowing the implementation. And so what you and Ada have said are really, really good. But if someone had said, write a 3-page on how you would implement this study, you would find that you're forced to think a lot deeply. So I like what you said, but you said that you would assume, right? But then you quickly changed it and you said, well, there would be teachers. You would have to confirm that there are teachers who have one teaching style and teachers who have another teaching style. Ada said it would be in a classroom. So Ada said different teachers teaching in a classroom would have different teaching styles. So she would interview the different students. And that's good. You can see that and if you ask another person, they would say something like, classroom A will be taught with teaching style A, classroom B will be taught with teaching style B. Then at the end of the year, we will compare their results. Even though it's the same curriculum, because it's different teaching styles, if A has better grades than B, then we can assume that teaching style A is better than teaching style B, you see. And then, so before you even jump to, so Ada said she's going to administer surveys. Before you even jump to surveys, you have to make sure that you understand the implementation that you are researching. So you're not just going to look and say, oh, we're going to do X, Y, Z with the data when the data has not been set up correctly. So in the example I gave, for example, what if it's not the teaching style? What if it is the teacher themselves that are better and not the teaching style? You see, what if the students in class A are just better than class B? You see, so those things are called confounders, right? But we're not going to talk about them. I want to make the point that before you jump into the statistical methods, you have to understand at a higher level implementation, analysis, results, dissemination. Okay, but let's imagine that you've used 2 schools. Ada, I see you've come off mute. Do you want to say something? Why don't you hold on to that, because we have 2 hours. I'm going to take off now, and then we're going to rush through. Okay, so let's imagine that you have your implementation great, and you've done this thing in 2 schools, school A, school B, and you've ascertained that the students in school A are the same as students in school B, and by the same I mean of the same academic and environmental quality. And then you trained all the teachers in school A to teach in style 1, and all the teachers in school B to teach in style 2. And at the end of the year, you compare their results and you compare them across different things. Now, there are 1,000 students in school A, 1,000 students in school B. Ada said she would administer questionnaires. Excellent. And if you are administering questionnaires, maybe to the teachers, maybe there are 100 teachers in both schools, you may not be able to interview or administer questionnaires to all the teachers, but you want to administer, or to all the students, you want to administer to a sample. So you see, this is what we said. You look at data, inductive reasoning, you look at data, then you make a high level conclusion. But for you to look at data, your data has to be representative of the population. You cannot interview all Nigerians. You cannot interview all Kenyans. So how do people say Kenyans believe XYZ? Kenyans believe, 50% of Kenyans believe that the economy is getting better. Did they interview 50%? No, they interviewed a sample that is representative of all the Kenyans. And that is why sampling is important, because remember, you're trying to make inferences about a population. You want to know whether teaching style A is better. You want to know what the perception of all Kenyans are, but you can only do so with a sample. And I'm going to ask and answer this question. Why? Because it is very expensive, very cumbersome to interview or to analyze the data across the entire population, such that sometimes you need to do it with only a sample. Now, your sample has to be unbiased. And so let's look at this slide. A probability-based sample is one which the likelihood of selecting each member of the target population is known. I like the technical jargon when I'm teaching epidemiology, but I also like to use everyday language. Basically, what we're saying is when you sample, you don't want to sample only certain people and leave other people out. For example, if you want to understand whether height is related to heart disease in the future, someone might go into the world and say, because I have a hypothesis that being tall is protective from heart disease, they would only sample tall people. That is a problem. What you want to do is you want to give everyone, irrespective of their height, a chance and an equal chance to get into your study. And that's the way that you are able to reach truth, because it's representative of the entire population, and then you're able to see tall people versus short people or shorter people and your outcome. And yeah, we'll talk about that later, but let's keep moving. If you have a question, feel free to raise your hand. So point 3 here, a random sample of a population are representative of that population, right? So we're talking about, we want to see whether school A is better, teaching style A is better than teaching style B. And I'm sorry, I'm jumping from example to example, but they make the point. And you cannot interview all the students. You take a random sample. Every student in that school has the equal opportunity of being collected into your survey. And you can assume, no, not assume, you can conclude that it is representative of that school. Okay, the bigger the random sample, the more information it gives about the target population. I'm not going to talk about why that is true, but it has to do with a reduction in outliers. The larger your sample, the more likely that is representative of the population versus the small sample. Yes, you can sample people randomly and say it is representative of the population, but the bigger sample is more likely to be representative of the population than a small sample, because a small sample is exposed to extreme values. Okay, let's move on. We're getting to 38 and we are already half hour. Okay. I'm going to skip this question because I already answered it when I told you about random sampling. Okay, so let's talk about the different ways that you can sample. I'll go through this quickly, and please feel free to ask the question. In simple random sampling, I'll give you an example. You're giving everybody, you don't care how people come into the population, you're giving everybody an equal chance. So for example, you could open your telephone directory. I don't know if people still know what a telephone directory is, and you say every number that ends with 1, I will call them up and ask them the questions. So your number is 080 or 090 or 247 or whatever. If it ends with 1, I will call you up. So that's random because most people get assigned their phone numbers randomly, and it has nothing most times, in fact, almost all the time, to do with what you're researching. Okay. A system. No, wait. Okay, I think I mixed a simple random sampling with a system. No. I'm correct. That's a simple random sampling. A systematic sampling is maybe you have a list of people, and then you say, I'm going to pick number one person, and then every fifth person that shows up, I will add them. So you can see that. So you pick number one, then you pick number five, then you pick number 9, or is it number 10? Then you pick number 14, and so on. So there is a system to your picking, that's a systematic sample. A stratified random sampling would be, for example, you want to capture maybe the same man, the same number of men and women into your study. You're going to say, okay, I'm going to randomly select 50 men, and then I'm going to randomly select 50 women. So you've stratified into men and women, and you've randomly picked 50 men and randomly. So that's a stratified. A cluster sample is, let's say you're working in, I'm going to pick a random, let's say you're working in Johannesburg, and you're trying to capture the data across all of South Africa, for example. You cannot go to, because for you to be quote unquote representative of all of South Africa, maybe you have to randomly pick people from all of South Africa, but you really cannot do that. So you're going to say, I'm going to box South Africa into clusters, into states, for example. And I am going to take all the states. I'm going to take people from maybe one state. That's a cluster. I would select people from that cluster, and they would be part of my study. Or you can say, I'm going to pick people from this state, and that state, those clusters, and then you assume that that is representative of the entire country instead of picking from the different states or regions. I'm not sure which they use in South Africa. For multi-stage sampling, what you do is you say, okay, suppose I pick a school. I pick a school at random. There are 10 schools in this city. I pick one school to study. In that one study, I will pick one group, maybe SS1, GSS1, 10th grade. And from that 10th grade, I would randomly pick these classes there. So you see there's multi-stage. You're sampling stage by stage. And then there's probability proportional to size. What happens in this is that sometimes, so suppose you're talking about this multi-stage sampling, I will pick this class, but some classes are larger than the other. What you would do is you would say, if a class is larger than another, I will assign, this is a little technical, but what you would do is I would assign the likelihood that I can pick a class is going to increase if that class or if that group is larger than the smaller group. In that way, what you end up with is a better sample. You don't end up maybe randomly picking only the small units that you're trying to research. There's a chance that you pick people into your study that are larger. The reverse is also the case. Sometimes you have maybe minority groups that you want to study, and you give them, oh, that's a statistical adjustment. It's not a sampling thing. But the reverse is also the case. You give them greater weights when they're in your sample. But let's stick to sampling. So you give people a higher chance of being pulled into your sample if the unit is larger, and that way you have a better sample. Okay, let's move on. So we're talking about stratified. So you can see, let's say the red is male and the blue is female. You can see that you pick 2 people from the red and 3 people, whereas from a cluster, you pick the entire, you say we're going to study Joburg, we're going to study whatever other Cape Town, and whereas we're going to leave Durban and the others alone. So you study those two instead of studying everyone. There's difference between stratified, random, and cluster sampling. Okay, I already talked about multi-stage. You can see, you pick a state, you pick a city, you pick a college, and from that college you pick individuals, different levels of sampling to pull together all these people at the bottom. I'm going to pause here and ask and see if there are any questions that you may have. Okay, I see Debbie has her hands up.
Yes, I just need a quick clarification. So on an earlier slide, you had something about probability-based samples, and then later you showed us a list of several types of sampling.
Yes.
Am I to assume that all of these are probability-based sampling methods?
Yes.
So
yes.
in that second slide that this one, are these all examples of probability-based sampling techniques?
Yes and no.
Okay.
So yes, and we're going to come to that, right? So, for example, think about this cluster. Remember that I said you work in, if you remember, I said you work in Joburg, right? And so maybe it's difficult for you to travel to the furthest regions. And you say, you know what? We can't go everywhere. We're going to pick, or we're going to flip a coin and just pick 2 or 3 neighborhoods, right? And so in that sense, it is a probability sample because you flipped a coin and picked 3 neighborhoods in Joburg. However, it's also not a probability sample because you're trying to infer about South Africa, and you didn't give all South Africans in all of South Africa the probability of being selected into your sample. Does that make sense why it's kind of a yes and no?
I hear you. I'm not sure I fully understand, but I hear your
okay.
Your
I'm going to try again. And maybe let's see. Yeah, let me try again. So what can I use as a really good example? So if you wanted to examine performance in a school, right? And there are 50 schools. There are 50 schools, right? And you say, you know what? I'm going to divide this into different neighborhoods. And instead of studying all 50 schools, I will study only the schools in one neighborhood. And I will study all the schools there. You see that you have, in a sense, you've clustered all the schools in one neighborhood and you have pulled them into your sample, but you have not randomly picked students from all 50 schools in that state. Is that a better explanation or no?
Okay. Thank you.
I'm sorry. Well, maybe I'll send something to explain it further. But that's they are and they are not. The best way that you can ensure a probabilistic sample, a thorough, is to have a simple random sampling. And I'm going to show you the point that I'm trying to make, right? Is okay. Most statistical methods assume the analysis is being conducted using a random sample. It's an assumption. Most times it's not possible. However, random samples are logistically challenging, they're expensive. Many research studies use convenience samples and treat them as if random. So that example I gave you of you're in Joburg and you select neighborhoods in Joburg because you can't go elsewhere or because you don't want to go elsewhere, it's a type of convenience sample. But because you can make some claims to a cluster. And let me use the states in Nigeria. This was Lagos, this was Abuja, this was Port Harcourt, Kano, Enugu. And you can't go to all of them. So you select these two as clusters. You divide them into clusters and you select these two at random from the 5. So in that case, you've not given the remaining the probability, equal probability of being ingested into your study. And so that is the problem. In a sense, it's a kind of convenience sampling. A very well-known convenience sample is the nurses or physicians' health studies in the US, because they know that physicians and nurses tend to be stable, and the sample is very large, and they tend to they tend to return questionnaires more than people. For years, they've collected data on doctors and nurses in the US. And a lot of people have used this data to run studies. But we know that doctors and nurses, or doctors or nurses, are not representative of the US population. And that is why it is a convenient sample, even though they use it to make inferences and conclusions about everyone in the United States. Another example is the cluster. You've probably heard of the Framingham study. So they selected Framingham as a city in Massachusetts in the US. It's a city in a state in a country, and they collected data on maybe 3, 4, 5 generations of people in Framingham. So that's a cluster, but they use that to make decisions about what healthcare or health looks like in the US population. So it's a cluster sample, but it's also a convenience sample. Why? I'm not sure the history of why Framingham was selected, but it was selected, and not everybody was given the opportunity to join in that study that has gone on for close to 70 years now. But let's move on. Okay, I'm going to pause here for 2 minutes. Please feel free to shout your answers or type them out in the chat. And I see that 2 other people have questions. So why don't we give Joe Vance the chance to ask a question, and Godwin, can you ask your question in the chat? But also everyone feel free to type in your answers to the poll. Joe, go. Is Joe in the room with us? Okay, maybe Joe does not have a question. Does Godwin want to ask his question?
All right. Yeah, thank you. Can you hear me?
Yes, clearly.
All right. So yeah, I wanted to ask about the multi-stage sampling.
Yes.
That at each stage, are we expected to use each of the sampling methods or techniques that you mentioned earlier, or are we also expected to maintain the same sampling method in all stages, or we can vary them in the stage? And also, is multi-stage sampling probabilistic, or can we use non-probabilistic and probabilistic methods in each of the stages?
So the preference is that you use probabilistic methods, right? So for example, and I'm going to use Nigeria because I do, and use the states in Nigeria. So think about Nigeria with 36 states, and you want to do a multi-stage. You want to understand whether people in Nigeria care about the reforms or what they feel about the economy. So you say there are 36 states. I'm going to throw a dart at the wall and pick 2, or I'm just going to randomly assign numbers to 36 from 1 to 36 randomly, and I'll pick 2 numbers. So that's probabilistic, because each state with 1 number has equal chance of being picked, right? And so in these states, maybe you pick 2 states, and there are 10 cities in each state, and you do the same, randomly assign numbers to them, pick 2 numbers at random, equal probability. So you see there is probabilistic even in that. And then you go say, okay, in the cities, I want to pick households, and you have a map of the different households, and you assign them random numbers, and you pick 3. And then from those households, you randomly pick a member of the household, or you say, in each of these households, I want to talk to the head of the household. In the former, you've randomly picked people. In the latter, you've restricted, so it's not probabilistic, because now you're talking to just the head of the household. So do you see how, even though it's multi-stage, it is probabilistic at every level?
Yes.
Okay, good.
Yes.
So to Debbie's point, I think maybe a sense of confusion might be that you expect that the definition that everyone has an equal opportunity, that is theoretically correct, but as we've seen, they're not always practically correct. For example, there's unrest in some parts of Nigeria. You will not say, because you're assigned, random numbers, if you pick those places where there is unrest, you have to go there. You're going to say, no, let's put that aside. In that case, you have reduced the likelihood that this is a purely probabilistic, right? But the whole idea is that you try your best to make sure that your sample is not biased. As in the example I gave of someone who's considering is height related to heart disease, and they go out and they pick more tall people or more short people into the sample. That is a clear bias, and that's what you want to avoid. Okay, let's go back to, I don't see, oops, I've shown you the answer. Oh God. I don't see any answers in the chat. So were you all waiting for me to show you the answers by mistake? Okay, let's see. I'm going to try to call somebody at random. You see, someone at random. I see Atahiro. That's not random. I like that name. That's why I selected the person. So if Atahiro Suleiman would unmute himself, can tell me the answer to this question. And if Atahiro does not unmute himself, Caroline Wangi can tell me. And if Caroline does not tell me, Humphrey Robb can tell me. And if Humphrey Robb does not tell me, my chief, Ibrahim Abioye, will have to tell me the answer to this question. Okay, if you heard your name, unmute yourself and tell me the answer to the question.
Hello, everyone. Good day.
All right. Hi. What are the
My
answers?
name is. Okay. Can I get some few questions, some few seconds to read on the question? So
take your
I
time.
understand better.
In the meantime, someone else can jump in.
Maybe I can give it a shot.
All right, let's go.
I would say C, using a roll of dice to select 5 clinics, and using a roll of dice to select 10 patients from each of the 5 clinics.
Yeah, I like that one. I like it very much. So why not B, for example?
Well, for that one now it's random. Why not B, for example? Using a computer-generated random number to select 10 clinics and selecting the first 15 patients that enrolled from each of the 10 clinics.
Hello.
Yes,
someone want to help?
Yeah, go ahead.
I go with option C too.
Option C too. Okay.
Yes, using a roll of dice to select 5 clinics and using a roll of dice to select 10 patients from each of the 5 clinics.
So why not A? Because A was exactly the example I gave when we talked about systematic sampling.
Yes, A is somehow similar with C, but in A, selecting the first clinic, you can do it based on bias or based on little bias.
The first patient.
The first patient. You can put bias in that. So that's why it is not probability.
So let me answer that. And I don't agree. In this is a best answer scenario. And I feel like you can make a case for all of them apart from D. So D says administered questionnaire to all women. So that's the entire population, right? But you can make a case for A, B, and C. I believe the strongest answers, however, are A and C. And I see Ibrahim is on the line, and he can tell me, and he can add to the conversation. So you pick one person. That list, no one knew, no one created that list in response to your research. It is you went to the hospital. You say, "Oh, can you give me the list of women attending your ANC?" And they gave you a list, and you say, "Okay, we'll start from number 1, and then every 20th person." There's no way that can be biased because the name has nothing to do with the time or how they appear on the list. On a list has nothing to do with the time, right? C, you're using dice. You select 5 clinics, and then you select using dice. You select 10. I really like that. B, you say you use a computer generated to select 10 clinics, and then you say the first 15 people that come. Okay, now I understand why B is not a good answer, because someone can argue and say maybe the first 15 people who come from that clinic are given preferential time, because what we are talking about here is the average waiting time. So maybe the first 15 people who come in are given preferential time or seen very quickly, or they take their time, and then the people who don't come. So maybe that's why I wouldn't like B. But if it was not a question that had to do with waiting time, you could say, well, we would take the first 15 people, because really, even in research, enrollment is quote unquote first come, first serve. You enroll until your numbers are complete, and then you move on. Okay, let's move on because of time, but I'm going to spend some time quickly looking at the chat. So if you selected D, you are wrong. But if you selected the others, I like your answer. And as long as you can justify your answer very strongly, and you get people to agree with you, you're
Sorry,
fine.
if I may,
Yes.
Ebuwa. Yeah.
Yes, sir.
Yeah. So the thing about the probability sampling is that for everybody in the population, you have to be able to calculate what is the probability that they are selected. And it doesn't have to be equal probability, but that probability must exist, right? And that's why that's B is not, because how do you calculate the probability unless you know that they are the first to come, right? Like, you have to first of all know they're the first to come. It's not based on, oh, you just go in this population and know that each person in the population has a certain probability of being selected, right? So that's the challenge with that B in particular. And the other thing to think about the B is that, for instance, people who come early to clinic might be meaningfully different from the people who do not. It might be that they are more well-to-do. It might be that they are more organized people. They wake up early. They're less representative of the rest of the population. So that's something that is important to also note. But yeah, definitely the question of probability is, is there a probability that this person, is there a probability that can be calculated that this person is selected? Yeah.
Right. And you're correct. It's I feel that it is not an absolute disqualifier, especially if we assume that people randomly show up to clinic, maybe they're not really different, and then you select. But the argument that you made is correct, right? Maybe there's something different about the people who show up early versus people who show up late, or maybe even the outcome you're looking for, like I said earlier, the waiting times will be different from those people who show up earlier than those people who show up late. But as we said, A and C are best answers in this case, but D is clearly not the right answer, and E is our I would say E is our least favored correct answer. Okay. But I think the point that Ibrahim makes is that you should be able to calculate, estimate for everybody what the probability is of being selected, and that way, selecting people into your sample, either based off of that or having known that probability is the way to go. Okay. Let's move. We are almost at the hour. Now, so remember, we're talking about implementation. How do you implement and how do you sample? And now, what do you estimate? So let's start with on the left, what we're talking about in terms of the population, right? Remember that we say we are trying to understand about a population. You cannot interview everybody in the population. Maybe you can sometimes in the census, who knows? The parameter that you're trying to estimate when you calculate when you're looking at a population, let's imagine that it is a mean, it is an average. So let's use our example about height. You're going to say, what is the average height of the men in Lagos? What does that mean? And that population mean is Greek symbol mu, right? And there is a standard deviation. In the next slide, I'm going to talk about standard deviation real quickly, which is the spread. And it is, I believe the sign is called rho. I don't know what it's called in Greek, but this is the sign for your standard deviation. However, when you're doing your studies, you're using samples, and we just talked about samples. So you're trying to make an inference about a population of 10 million people, but you interview 150 people. Your mean value, or you measure the height of 150 people, your mean value, X bar, is in, I believe, your Roman numerals. X bar, this is called X bar, and your what you call it, your standard deviation in your sample would be an SD. Now, let's talk quickly about this second point, right? The sample mean may not necessarily equal the population mean every time. This is uncertainty. And this is an important statement because we're going to talk about your central limit theorem, and why we are able to use samples to talk about populations. So remember what we said: if you sample correctly and it's representative, of the population, you will most likely be able to reach the truth about your population. However, it's not all the time that you will be correct. So for example, you probably have read papers where they say, oh, XYZ, Ibrahim et al. Found that the average height of men in Lagos was 5'8". Another person found it was 6'2". Another person found it was this, it was that. What is the truth? We may not know, but we are, and this is where the central limit theorem comes into effect. But we have a level of certainty that this is our best guess of estimating the average or the mean. Okay. Point 3 is, I think I should skip this because we're going to get to central limit theorem. Let's jump right to the mean and the standard deviation. Now, why is the standard deviation important? Standard deviation, for me, helps you to understand the standard error, and we'll talk about that in central limit theorem. And when you measure, suppose you had a sample of 100 men, and you're trying to measure the average height of these men in Lagos. You want to make an inference, a conclusion about the average height of men in Lagos. And you measure one person, they could be 5'8", another person could be 5'9", another person could be 6'2", another person could be 5'4", another person could be 4'11". And then you measure and you take the average, and your average, this is your normal distribution curve, and your average is here. Imagine your average is here, but there will be some people who will fall here, some people who fall here, and some people who fall here. And so you're like, wait, if I say that on average, the men in Lagos are 5'8", why are we seeing people here and people here? 5'8" may not be representative of these people here. And that is why you have to quantify your mean with a spread. You're going to say basically that the average height of the sample is 5'8", not of men in Lagos. I'm sorry, I've been talking about the population, but this is the sample. The average height of the men in the sample is 5'8", but the spread plus or minus 1 foot or plus or minus 6 inches. And that gives you a sense of how everybody in that sample falls, So plus or minus, there's an example that I give later on that I think is funny, but you want to quantify. And why is this important? It's important because you want to be able to get a sense if the spread is really, really wide. What if there's a lot of people on this side, 411, and what happens is they are pulling your mean to the left? Or what if there's a lot of people on this side and they're pulling your mean, to the right? Your spread is going to be wider, depending on where everybody falls, or if everybody is closer to you here. And so your spread helps you get a better sense of what your mean does. Okay, so now we've talked about sample, we've talked about what we are estimating. Let me go back here and say really quickly that it's not always a mean that you're estimating. Sometimes you're estimating what you call a mean difference, or sometimes you're estimating, a proportion. Sometimes you're estimating a ratio. It's not always a mean, and we're going to talk about that a little probably in this class, but I think a little about it in this class, but in other classes, definitely. Okay, we're at the hour. Let me pause here and ask a question. Is everyone okay so far? And do you have questions about what we've learned so far? Okay, I see 1 thumbs up. I see 2 thumbs up. Okay, I will take 2 thumbs up as 5 stars. Oh, 3, 6 stars, then 6/5. Okay, you guys are trying to just make me happy. Okay, let's go back. So we've talked about the basis of research. We've said it's for decision making. We've said it is to establish truths. And Ada said it's also to predict and forecast. We talked about inductive and deductive reasoning, and we said that in inductive, you're looking at data. And I caution that even though this is the quote-unquote best way to reach conclusions, I told you the story about the chicken that gets slaughtered on Christmas Day because he was looking at the data and thought that they were feeding him indefinitely. Or feeding her, I don't know, I think chickens are female. And then we started talking about implementation. You need to understand how a study is implemented before you jump in. And so think about it before you go in and start saying, we will do this, we will do that, we will compare this. How do you get to that point, implementation? And then we talked about sampling. Sampling is part of implementation, but it has statistical concerns. And the takeaway to repeat Ibrahim's point, when we're talking about probabilistic sampling, we want to make sure that we know that everybody has the probability of being pulled into this. And so that's something you look out for. But I also made the point that sometimes, we made the point, it's on the slide, not all samples are quote unquote 100% probabilistic. There are a lot of convenience sampling, and some people are excluded right off the bat. Okay, and then we talked about the effects that are being measured. There's the mean, and there's the around it, the spread around it, and this, in fact, some people say this is one of the issues with your scientific method, but we'll talk about the central limit theorem and how it overcomes this issue of outliers, of results that may not be indicative or correct about the population. Okay, so now you've implemented, you've sampled, you've determined that we're looking at Ada. Let me put you on the spot. Let me ask you a question, Ada. So feel free to unmute yourself. And if someone wants to volunteer, please you can raise your hand and you would be the person. I see a name I like, Babale Sofian. So if you want to come off your mute, you said selecting the first, I believe, is not as probabilistic as it should be. And that's the point that Ibrahim also made so good. So you have implemented, you have thought through what you're going to be measuring. So the reason I called Ada is this: she was the one that first answered the question. So when you conduct your survey, what exactly will be in your survey? What are you going to be measuring when you're comparing two teaching styles across different schools? Is Ada in the room with us? Does someone else want to answer that question? Okay.
Maybe I will just make an attempt.
Let's go. Yeah, let's do it.
If the survey was or is going to be administered to students,
what would your survey be measuring?
The comprehension level.
So you would measure comprehension level, okay?
Yes.
Yeah. How would you measure comprehension level?
That's so I'll ask some questions relating to the curriculum.
Okay. So you provide a quiz.
Yes.
So you see how, so we started with questionnaire. Now we're saying quiz. Now we're saying comprehension. The point I'm trying to make, right, is understanding the scientific method has to be combined with understanding implementation, right? And has to be. I think that's the point. Okay, let me give Jumoke Abdul Wahab a chance. Feel free to unmute yourself, or Debbie, feel free to unmute yourself, and we'll go forward. So you're the star. You're both the stars of this section. So let's talk about hypothesis. And the reason why I asked that question, what are you measuring? Because you have to have a hypothesis, and you can say, oh, teaching method A is better than teaching method B. Maybe that's your hypothesis. But in what way? And then Godwin said the students are able to comprehend with teaching method A than teaching method B. So your hypothesis is comprehension levels are improved in A versus improved in B. But listen to what I just said. I didn't say comprehension is better in A comprehension than B. I said it's improved. That means if everybody started, if the people in A started at 5, their improvement will go to 15. Whereas if the people in B started at 5, maybe their comprehension would improve to 7. So you can see what you're doing is called a difference in difference. You're going to say the improvement in A versus improvement in B. What is the difference between those two differences? The point I'm making is that you have to be clear on implementation, but you also have to be clear on what you're measuring. So you've been told that you measure the mean, you can measure the proportion, but the mean and proportion of what? Okay, so now we're clear. Let's go with Godwin. I don't think that Jumoke or Debbie have unmuted themselves, but I'll still continue to ask them questions. Maybe, perhaps they would answer and unmute themselves. So now you have clarity on what it is you are measuring. We want to measure the improvement in comprehension between school A and B based on the type of teaching style that we've implemented in A versus B. Can you see that it's becoming complex without becoming complicated, right? You have a clear statement. Our hypothesis is that, and I'm going to make a clarification, but flow with me. Our hypothesis is that teaching style A improves comprehension more than teaching style B. Okay, now that is called a research hypothesis. That is what you're hoping to see. But in statistics, we don't start with the research hypothesis. We start with the null hypothesis. And this null hypothesis basically assumes, this null hypothesis basically assumes, wait, where am I? What's going on? Okay, this null hypothesis assumes that, so you see this line, it says the null hypothesis assumes the relationship is not true. Debbie, Jumoke, what relationship are we talking about? Do you know? Can you tell me, or can anybody on this call tell me what relationship are we talking about? I see someone put something in the chat. Maybe the person who put something in the chat tell me. Oh, is the research hypothesis the same as alternate? Yep, I like that. Oh, and Ibrahim said that sign is called sigma. Okay, so Debbie started to talk. Debbie, go on.
Well, I was about to say that the null hypothesis is essentially saying that there is no difference between, in this particular example you have given, the outcomes from teaching method A and teaching method B. That's the null hypothesis.
Right. Okay, great. So you're saying that the null hypothesis, when we say the null hypothesis assumes the relationship is not true, we're saying that we start with the assumption that teaching style A does not improve comprehension more than teaching style B, or that they improve at the same, or they don't improve at all. Whatever the case is, there's no relationship between teaching style and your outcome, which is an increase in comprehension. So
yes,
if you think about this, right, you can understand it in different ways. And now this is another nuance that I'm bringing, where you have to be clear in your hypothesis, right? So one of them might be, does teaching style A even increase comprehension at all? That could be a hypothesis. Because let's say teaching style B was your standard of teaching, your regular teaching, and teaching style A is your new one. So you want to ask, does it even improve it at all? And another one could be, does it improve it significantly more than B? You see, those are two different things. One is, does it work? The other is it better? And so clarity in your hypothesis and your null hypothesis, for whichever one says, no, it doesn't. There's no relationship between A and comprehension, or A and improved comprehension. So yes, you can have an alternate hypothesis, which is your research hypothesis, which says that yes, it does, it works. Number two, it works better than B. Okay, let's move on. If no one has a question, we shall move. I think I've made all the points here. So yes, let's try to move on. Okay, so now, so you've established your hypothesis. We're starting from top. You've done a really great program. You've implemented. You're clear with your hypothesis. Now, this is the statistical part. You state your null and your hypothesis, your null and your alternative, or your null and your research. You specify the significance level. This is a statistical theme. We'll talk about that. Based on your significance level, you compute a test statistic. Now, a test statistic basically says, it could be a Z statistic, it could be a T statistic. It basically says, this is a value that we're going to use to judge whether there is a relationship or not. You know, and your test statistic relates or is converted. I'm going to use the word converted or reveals a p-value, and that p-value is what you use to determine. Conventionally, we have said above this level of the p-value, we will choose to determine. We would choose, or we would agree that there is no, beyond this p-value, that there is no relationship. That is, and that that p-value, that threshold is called your significance level. Your p-value is what you compare with your threshold to say, I agree there is a relationship, or I fail to reject the null and conclude, that there may be, that we don't have evidence that there is a relationship. Okay. Let's go. Let's see if we're going to, let's go into this a little more in depth. Okay. So you've made an observation, you formed the hypothesis, you collected your data. I like the way this is positioned, right? You collected your data after you formed your hypothesis. So this is your primary research. In secondary research, your data was already collected, right? And so your hypothesis, you still apply to the data, but you've collected your data. And the reason why I said I like this is that imagine that you're talking about you're comparing A to B, but you're not clear on whether it's an improvement in cognition, an improvement in comprehension, or just outcome scores. How do you know what data to collect? So I think it was Godwin that said, if we're testing comprehension, we will give them a quiz. If you didn't know that, I don't know, maybe there are other ways to test comprehension, but imagine a quiz was your best way or your only way. If you were not clear with your hypothesis, you would not know that you are to administer a quiz. And that's why I like the way that this is arranged. The problem with secondary data is sometimes you have a hypothesis, then now you have to go and look for data that has been collected. Okay, now you're ready to disseminate. I think that we should come back here. Maybe an example is needed, but like I said, we're just talking about the principles here. But subsequently we'll talk a little more. And we'll maybe drill down with an example. So, but let me harp on this just a little. So let's use an example of the heights in Lagos. Let me ask Godwin, because he's quick to respond. Can the average height of people in Lagos be 0 feet? It's not a trick question.
No, in my opinion, no.
No, is it your opinion or is it the truth? Okay.
No, actually.
Okay, good. So sometimes I tell jokes, but many times my jokes serve a purpose. So you're thinking about what is the height of the people in Lagos? What's the average height? So your hypothesis, Godwin. So what is your null hypothesis if you're looking for? And remember, if you remember, I showed you a slide that sometimes your statistics could be descriptive, could be inferential, could be predictive. So first question to you, Godwin, you got an easy one. So let's do the hard one. If you're looking at for the average height of people in Lagos, is that descriptive or is that inferential?
The average height.
Yes.
I would say it's descriptive.
It's just descriptive. Okay, good. It's going to get harder. So stay unmuted. Okay. So now you want to do a study and you want to do something a little bit inferential, and it's about the height of people in Lagos. What do you think your hypothesis, your null hypothesis, and your research or alternative hypothesis will be?
It could be that
you have 10 seconds. Otherwise, Debbie's going to jump in and give us the answer.
It could be that the height of young people in Lagos is higher than the heights of older people in Lagos.
I like that. I like that very much. So your research hypothesis is what?
Is that there is is significant. Now how to frame it is a challenge, but yeah, there.
So which are you trying? You're saying that the height of older people,
younger people is
higher.
Yeah.
Oh, you're saying younger people 40 and below are
Yeah.
higher than the height of people. Okay, good. So that's your research hypothesis. So you perform a t-test. You get your sample, right? You go into the world and you pick people at random. And then you say, okay, let's find their age. If you're 39 or below, stay this side. If you're 40 and above, be on this side. Then you measure their average heights, right? And then you compare using a t-test. And then you say, well, the height of younger people is 5.6, and the height of older people is 5.4. Keep that in mind. We're going to get somewhere with that. 5.6, 5.4. Now, you generate your T statistic or your Z statistic, and you check the p-value. And statistically, we've agreed that a p-value of less than 0.05, you will agree that there is a relationship, aka you will reject the null, right? And if it's 0.05 or up, you will fail to reject the null. Okay, good. So now you've gotten your p-value, and your p-value is 0.03, right? What will you decide, Godwin?
Yeah, I will decide to. Oh, I forgot the explanation you gave earlier. I'm trying to refresh my brain, but I'll basically decide.
Will you decide that there's a difference or not?
I'll decide that there's a difference
because your p-value is less than
0.05.
So you will reject the null that is all right. Debbie was ready to give that answer, but good for you. Okay, let's move on. Does someone have a question? Okay, so remember what we were saying. So we've moved on from there. We're going to come back to it, and I'm going to do this in 14 minutes. So remember what I said, that sometimes are we looking at a ratio versus a difference? A difference is 5.6 versus 5.4. That's 2 inches. A ratio could be the risk in exposed divided by the risk in the odds of the risk in the exposed divided by the odds of the risk in the non-exposed, right? And then the direction of the effect and the statistical significance. So the direction of the effect is there a protection? If we're looking at height and the outcome is cardiovascular disease, are we saying that height is protective, or are we saying that height is a risk? And of course, your statistical significance. So you're going to say, for example, that if you use a ratio, you're going to say that tall men have 2 times higher risk of cardiovascular disease than shorter men. That is your ratio. They're going to say that what I just said is actually captures the direction. Then you're going to say there is a higher risk. It's a 2 times higher risk. That's your direction. Then you say we found this to be significant at a p-value of 0.03. Okay, so now, the p-value, excuse me, is the probability that you are wrong. So let's forget about this. I think I put this, or we put this, we're just messing around with this, but it is very true. Your p-value could say, your p-value says, if basically we've agreed that if your probability of being wrong is less than 0.05, we can agree that you're correct. And this has to do with uncertainty, but we're going to move beyond this, and because we're going to talk about the central limit theorem as we move on. Okay, so p-values are not hard and fast, and we're going to talk about why p-values are not hard and fast when we're comparing your clinical significance with your statistical significance. Okay, and remember that remember that we agree what the threshold is. I'm sure that in the research that Ibrahim does, Dr. Abioye does, he's seen studies that use a 0.1 instead of a 0.05 statistical significance, right? So we've agreed that we've agreed that we're going to use mostly 0.05, and this is why you should state it in your research paper, you know, that this is the threshold. A lot of people don't state it anymore because we all assume that it's a 0.05. And then in general, report your exact p-value, and if your p-value is very, very small, and you can say it's less than 0.001. I think that the people who are teaching the actual analysis will tell you how to arrive at this less than or what number to put here, but we won't do that today because we're just talking about principles. Okay, so sometimes let's talk about errors in testing. And let me take a deep breath so that I don't mix up my error 1 versus my error 2. So let's start with, of course, error 1. So type 1 error. What you should know about a type 1 error is that sometimes there is no difference, but for some reason you find that there is a difference. That's a type 1 error, right? It is a false positive, right? And it means the positive result we obtain from our study is likely to be wrong. Remember what we said earlier, that your p-value is your probability that you are wrong. So there is a chance that you are wrong, even when your p-value is less than 0.05. And the chance that that happens, you commit a type 1 error. And many times a type 1 error happens when you're doing multiple testing. So think about it. If there's a 5% chance that you are wrong every time you test, by the time you test 20 or 100 things, you know, the common thinking, and I've not proved this probabilistically, but the common thinking is that at least 5 of those conclusions will be wrong, because you've tested 100 times. There's a 5% chance that your result is wrong. And so every 100 p-values you get less than 0.05, there's a likelihood that about 5 out of them are wrong. You might say, well, I have not done 100 tests, but you are part of a group of people doing 100 tests. It's difficult to explain, but imagine that we were all every research you did was a simulation of that research that could be done. So you could be finding a wrong result when you're doing your own research. And so you have to be careful. And what you do is you look at other people and think about, well, is this wrong? Is this right? Did other people find this? And then you cannot conclude that it is wrong, but you can describe and say other people found XYZ. Our findings found something that is the opposite. So I talked about the 0.5, you know, and what your alpha is, what your threshold is. So let's talk about your type 2 error. Your type 2 error is when there is actually an effect, but you don't find that effect. So think about this. You're looking for a pin on the floor in your room, but the light is poor, right? The pin is there, but you don't find it because you don't have enough power in the light, or you don't have a bright enough light to find that. That is a type 2 error. So that leads to a false negative. You're going to say there is no relationship, but there really is a relationship. And this ties to power, and that's why I use using a light source. So we're going to talk about power now. Okay, so let me elaborate on that analogy that I just said. Think of power the same way you think about a torch. You know, if the light is dull, you're unlikely to see things that are already there. That's what power is, you know. However, and this is a technical thing with power, what happens is your power is pulled in different directions by your effect size. What is an effect size? That difference. Remember when I said keep in mind 5'6" and 5'4"? That's 2 inches. That's small. This is 2 inches. It's really small, right? So if your effect size is small, if the pin you're looking for is tiny, you need a lot more power from your torch to find it. Okay, your sample size. Now, what will make it clear that younger people in Lagos are different in height from taller people in Lagos when the effect size is only 2 inches is how many people. Remember at the beginning of the lecture, we talked about how your sample size helps you to prevent against swings in your extremes in your data. So what happens is a larger sample size congregates around the mean. The larger sample size is, the smaller your spread is. I think somebody, maybe me, in the next lecture will teach you about how the mean differences are obtained, right? But if you have a tighter spread around your mean, you are more likely to identify a smaller sample size than if you have larger spread. So you see that your sample size also impacts your power, your significance. So remember, we just talked about it. We said if your significance is 0.5, that is a stricter, 0.05, I beg your pardon, that is a stricter level of rejecting your null or failing to reject your null than if your significance was 0.1. So 0.1, 0.05, you know, and of course, statistical power is what we've talked about. We say it's the probability of accepting the alternative hypothesis. Basically, if it is true. So basically, we're saying, what is the probability that we are actually reaching the right conclusion? And you can measure that statistically. I'm going to pause here. I'm going to take one question, maybe two, and then we're going to move on. Oh, someone said take the effect size again. And Debbie says, I'm curious to know under what circumstances would the p-value be different from 0.05? So, so far, I've not had any research that has used anything less than 0.05, but I believe that in nutrition, it depends on the field. I believe in nutrition, some studies have used the 0.1 or use a 0.1. I think that and then let me ask Ibrahim, because Ibrahim's focus was in, or still is in, nutrition, and maybe you can answer Godwin's question about what is the standard parameters for selecting. My answer to that is that the team tends to agree, that let's use 0.1 here versus 0.05, but I will, depending on how strict they want to be, but I will throw this question open to Ibrahim if he has an answer as well.
Yeah, thanks, Ebuwa. So usually we'll do 0.05 because that's the convention, and there's a movement increasingly to losing the threshold, like the strictness of the threshold, right? So people are generally saying report the p-values and let the reader decide. So that's one view. In meta-analysis, we often use 0.1, not 0.01, 0.1 when we expect that there is not enough power, right? For some tests, we would then use 0.1 because those tests we know that there's not going to be enough power, either because there's too few studies. And so if you find something at 0.01, then you know that that's whatever you found is likely to be true, right? Unlike because if you were waiting for 0.05, you would never get to it because there's not enough statistical power. Right. So in those scenarios, we will do 0.05. 0.0, we'll do 0.1.
0.1.
0.01 is probably stricter than usual. Maybe there are stricter p-values that you would use in interim analysis, right? But otherwise, I think that it's not usual to use 0.01.
Right. Okay. So 0.05 or 0.1, very, very strict. 0.01 may be in an interim analysis because okay. And so Jerry asked about pick effect size. So your effect size is what we talked about. You want to know if younger men are taller than older men. Your effect size is that mean difference. You want to, so the difference between the average height of younger and older. You want to know whether height is protective or a risk factor for cardiovascular. So you say that the risk of cardiovascular events in shorter men is higher than in taller men. That ratio, when you divide that ratio, then you have your your HR or your RR of 2.0. That is your effect size. Or you want to say it could be a difference in proportion. You want to say 50%, how do we say it? So that's the chi-square, right? You say 60% of people in group A scored 10 out of 10 in the test. This is a comprehension test versus 40%. Is that 20% difference? Is that 20% difference statistical significant? So that is your effect size. You would say there's a 20 percentage points increase in group A versus group B when you apply this new way of teaching. Okay. Let's do this. Let's do this poll, and we will take less than 5 minutes to do the poll. Put your answers in the chat, and then this measures if you're able to grasp, you know, the relationship between power, sample size, effect size, and put your answers in the chat. Or I'll just ask Jerry to answer on behalf of everybody, so we can move on. Jerry, what's the answer to poll 5?
I'm actually even still reading through it.
Let's go. It's okay. Okay. Anybody else can jump in and give the answer. So Godwin, you've asked a good question. I'll take that question and then we'll move forward after we get the answer. So anybody feel free. I put Jerry on the spot, but that's not the idea. Anybody. So Brandwell says the answer is C. Brandwell, can you tell us why your answer is C?
So I have used the elimination method.
Okay, tell us.
Specifically from B,
Mm-hmm.
because if the department requires that they need to be very sure of the difference and ask you to use the alpha is equals to 0.01, I think Ibrahim tried to mention, then the sample size there will be even larger, not fewer women. Then in that case, D and E are eliminated and I'm left with C.
Okay, let's go from the top, right, and see whether this everybody. So 10 minutes. If the minimal difference was 20, it was 20 minutes, right? So that's the effect size, right? Now this effect size has been reduced to 10. Do you think you're going to need more people for a smaller effect size or less people for a smaller effect size? Brandwell, questions for you. So I'll just tell the answer because of time. So I believe you're going to need more people to see a smaller effect size. So you would need to recruit more people. The second one is, if the department requests that they need to be very sure of the difference and asks you to use a smaller p-value, you would need to recruit fewer women. No, you would need to recruit more people. Otherwise, so that you increase your power and to see a difference. If the department decides that they prefer you to use a power of a beta of 30, so remember that your power, I didn't say this earlier, but your power is 1 minus your beta. So that is, you have less power. You would need to recruit fewer women. I don't think that's correct. I think that for you, if you have lower power, you need a higher sample size. So which of them is true? Did I mix up B? If the department requests that they need to be very sure of the difference and they ask you to use, you would need to recruit. I don't like any of these answers, but
you don't like C?
I don't like C. If the department decides that they prefer you to use beta is 30, meaning you have a power of 70, I think you want more people if you have low power. If the minimal, let's see, when I was looking at this earlier, I think I agreed with the what you call it. So let's look at it and see what our answer is. If the department decides that they prefer you to use a power of 70, you would need to recruit. No, I don't agree that. Right now, I don't agree that that is true. Maybe I agree.
I think it's true. No, maybe probably the issue
Tell
is,
me, why do you think it's true? If your power
because
is
it is actually an inverse of B. If you say that beta is equals to 1 minus alpha,
no,
it
beta
means
is
that
equal to 1 minus power.
Oh, okay. Then let me hold my peace first.
So, Ibrahim, help us here. Am I wrong?
I think you might be reading it. Maybe the way you're reading it is why you're thinking that it's wrong. So basically, with low power, so if you're going to make a decision, if you require low statistical power to make a decision, then you can go away with fewer people. If you want higher statistical power, that means you want to be more certain, i.e., so you need more people in your study. So if you go from 70% to 90% power, you will need a larger sample size.
If you go from 70 to 90, you will need. So if your power is low, so let's imagine that your power was low. You would need a lot more people to be able to prevent you from committing type 2 error.
I mean, so if your power is low, you will have. So think about it like this. I think the way you're thinking about it is the problem. The concept is the same.
Yeah.
If the power is low, the power is low because there are few people.
Okay.
Right? If you take two studies that have the same effect size, if there are few people in one group, in one study, the power will be low to detect that effect size. If you increase the number of people, the power will increase.
Right.
If you reduce the effect size, a small effect size is harder to detect, right, at the same power.
Okay.
So if you increase the sample size, it's easier to detect a small effect size because then you have higher power.
Say that bit again. If you
reduce the effect size,
you need higher power.
You need higher power to detect it. That means you need more people.
That means you need more.
Yeah. So if you have a let's take a drug, for instance, whose effect is small.
Okay. For
that drug to detect and for you to detect an effect of that drug in a trial, you need a much larger sample size.
Right.
So let's even talk about like death, for instance, right? If you're trying to prevent death, say you're providing antihypertensives and you want to prevent death.
Mm-hmm.
Because before you go from antihypertensive to death, you need a much larger effect.
Okay.
But that effect, you don't have it because the effect is small.
Mm-hmm.
Right?
So you need a larger sample size.
You need a larger sample size to detect the effect of death. So that's why they're going to study, and that's why something like the COVID vaccines, for instance, needed like 30,000 people in their trial.
Right. Okay. I think the point you made earlier captures this, right? It's like if we read it as written, if the department decides that they prefer you to have smaller power in this study, then you will recruit fewer women, right? But here's the point: the power to detect, or the likelihood that there is an effect size of this 20 minutes, right? Is not dependent on whether we agree or decide on how we decide the power. The power is there based on our sample and effect size, right? Not whether a department agrees with it, or whether a department sets it up. So I think initially I read it the way you said, if the department decides, but when I was reading it just, I'm like, I don't know that just smaller power automatically determines that you need a smaller sample size. I think it's the other way around.
Yeah, the way the question is written is for, say, you're a statistician calculating the sample size.
Yeah.
And these are the parameters you're going to use to calculate the sample size that you need.
Yeah.
That's how the question is framed.
Okay.
Yeah.
Okay, we'll take that. So I see Jerry has his hand up. Ask your question. Let's move on.
Yeah, quickly. Can you hear me?
Yes, sir.
I'm actually struggling with network at some point. So I just wanted to find out, what is B actually? Beta. What is beta? Is beta the power?
No.
Or beta is something else?
1 minus beta is your power.
Okay, so what is beta?
So your beta, what is your beta? It is your chance of making a type 2 error, isn't it? Oops, where am I?
That's correct. Yeah.
Yes, it is.
That's correct.
It's your likelihood that you're going to make a type 2 error. Excuse me.
Actually, with that definition, Doc, you automatically then means you need fewer people because you have increased your chances of making type 2 error. Then you need a smaller sample size.
Yeah, so I agree, right? But I don't exactly like it. Wait, am I showing my slides in presentation slideshow? Let me see. Okay, so I think that what we can do is, oh God, I made a mistake again. Okay, so let's go ahead and I'm going to agree with everyone reading the statement correctly. But I think that we should be careful not to assume that we are the ones who determine what the power to determine a sample is. It's a little difficult to explain because your effect is either there or it's not there, right? And your effect is what drives your ability to, your effect size and your sample size are what drives whether you will have power to determine, not the other way around. Your power does not drive your ability to see an effect. Is that right? Your power? You cannot say, oh, I'm going to see an effect at 70% power. And someone says, no, I will use 60% power to see an effect. An effect is either there or not. The question now becomes, does your sample size and your alpha give you enough capacity, enough power to determine that effect size that is there, because your effect size is the truth, and your truth is the truth. Your truth doesn't change based on power. Your truth is there whether you like it or not. But let's move forward. It's a kind of it's not a philosophical discussion, but let's not spend too much time on that because of time. Okay, now we're going to talk about the central limit theorem, right? And remember when we're talking about your sample and we talked about your spread, and we said that you have a sample mean, and then there are people that could be on either edge or of your normal distribution, or there could be people that are around your mean. Okay, we also now imagine that your population is a lot of people. I said something earlier that sometimes when you conduct a study, you have to see yourself as one element in a simulation of multiply repeated studies. And that is why even without conducting 100 tests, your results can actually be wrong. You can have a type 1 error. It's not something you did, it's just the probability of probabilities. But imagine that instead of you being instead of you being part of the simulation, you are actually conducting the simulation. So you take a sample from a population, you conduct a test, you find your mean, you put those people back into the population. Did someone want to say something? Okay, I'll continue because time. And then you go back and then you sample again, and then you find the mean and you record your mean. And this is called sampling with repetition. That means you throw people back into the lot and then you sample again probabilistically, and then you take your mean. Now, if you do that 30 or more times, the people say 30 or more times, and you plot those means will give you a perfect normal distribution, and the mean of those means will be the mean of the population. So remember when we were saying earlier that we believe or we assume the scientific method to be very valid. It is because of the central limit theorem. If you repeat an experiment multiple times over, the mean of those means will approximate or will be exactly the population mean. And this is why people conduct meta-analyses, because they are basically finding in theory, or essentially they're finding the mean of the means of the different studies that have been conducted. Now, and not only do you have the mean of the means to be the population mean, the standard deviation of your mean is going to be your standard error, right? And so we have this point where we say the standard error is the standard deviation of the mean of the sample means, which is the population mean. It's a tongue twister, but I just explained it now. There is a 95% probability that the mean lies between your mean plus or minus, because it is a normal curve, 1.96 times your standard error, to the mean plus 1.96 times your standard error. What this is doing is, even though the standard limit theorem tells us that your mean of means would approximate your population mean, there is always, and there's also a chance of error. So in statistics, we're constantly talking about uncertainty. There is uncertainty that you could be wrong. And so you calculate a 95% confidence interval around your mean, or around your mean, and you'll be able to say that we are 95% certain that your population mean falls between your lower bottom of your confidence interval and the higher end of your confidence interval, which is estimated by your sample mean or your mean difference plus or minus 1.96 plus times your standard error. This is an assumption, by the way. This is an assumption because your sample mean is not the mean that you conduct with your central limit theorem. It's a little difficult to explain, right? But I think that we have proof that there is a 95% probability that your sample mean plus or minus 1.96 times your standard error captures, you have 95% certainty that it captures your population mean. And that's because the mean that you calculated is one of the means. If we had more time, maybe we'd explain it. It's one of the means in this normal distribution that is created when you conduct that simulation again and again and again. Any questions there? Okay, no questions. It's either we all understand it or we don't all understand it. Okay, so I just explained the central limit theorem, and let me say one more thing. Maybe it will put things in perspective. So imagine that you've done your repeated sampling. You've done your repeated sampling from a large sample, and your mean, your own experiment. So now you have to split yourself into two. In an alternate universe, you've done this thing 30 times, 300 times. But in this universe, you've done only one study. Now, that one study in the alternate universe is one of those simulations. And when you plot that mean, let's say it falls right here, you see that when you add or subtract your, not here, when you add or subtract your 1.96 times your standard error, it will capture this 0 point, which is your population mean. And that is why we have a high level of confidence that you are capturing. You have a high level of confidence that your mean plus your confidence interval encompasses the actual population mean. It's a little tricky. Apologies if I didn't do a good job, but that is how to think about. That is the confidence that we have when we do only one experiment and we extrapolate. Remember, we're talking about inferential inferences. We're extrapolating from a sample to the population. So tying everything together is if your sample is representative, if you've implemented you properly, if you have good hypotheses, you've estimated your interval, you've estimated your effect size, you have your good power, or you have the right amount of power to prevent a type 2 error, right? What you're going to find is that mean of your sample, based on the central limit theorem, because it falls anywhere, well, maybe not outside 3 standard deviations, but when it falls within that 95% of your curve for your central limit theorem, you have 95% certainty that your upper and lower limit and your mean capture the true population parameter. It is an assumption based on the central limit theorem. Okay, so I explained that one before we got to the slide, and I already talked about the confidence interval. But let's talk about why the confidence interval. Remember, someone said that research is for decision making, right? And this is a joke that we put in here. So we said that imagine that you're going to make a decision about how to fund healthcare, and someone says the mean average healthcare amount is between 800 to 1,500, but our best guess is 1,000. But we believe that 800 to 1,500 captures the population mean. That means the population mean can actually be 1,500, and that is a 95% certainty, not 100%. If you're going to make a budget decision for how to fund healthcare, you wouldn't use 800, which is the lower end. You wouldn't use 1,000. I wouldn't suggest that you use the 1,000, although that's your best guesstimate. I would err on the side of the upper confidence, because now we're making a decision. Because what if you budgeted 1,000, but we know that it could range, the population mean could range from 800 to 1,500. This is how I think about a confidence interval for decision making. But if you're thinking about what is on average our best guess would be your point estimate of 1,000. And so the academic definition, we're 95% certain that the population parameter falls between the lower and upper boundaries of a 95% confidence interval. Our best estimate is the mean value that we got from our sample, not from the population, because you did not measure the population. Okay, we're almost at time. I think we can jump this and talk really about clinical versus statistical significance. So remember when we said that the difference between the young people and the tall people was 2 inches. Okay, so think about this for a second. We had a p-value of less than 0.05 and we were excited. But how much does 2 inches in height mean? You know, if you're saying that, for example, are saying that height is a protection from cardiovascular, are we really saying, and this is a bad example, are we really saying that those 2 inches are enough to cause that protection? Maybe not. I don't know. Let's use a better example. And I think the better example is with hypertension. I think we have hypertension. This is a question here, but let's use hypertension. So you do a trial and you find that your hypertensive medicine reduces blood pressure versus standard of care by 2 millimeters of mercury. 2. And you are statistically significant. You go ahead and you publish that result. The doctors are going to come back to you and say, yes, it's statistically significant. But if a patient is 170 and he reduces by 2 to 168, that patient is still hypertensive. There is no value of this 2. And people would say, if you give me a drug that reduces blood pressure by 10, I will start to consider it. Don't worry about putting them in normotension. Just reduce it by 10. The doctor will say, I will start to consider it. So you see, the doctor has said, this is clinically significant for me, a 10-point reduction versus a statistical reduction of 2 that is statistically reduced. And this is to the question that Godwin asked in the chat, you know, where you say, puts the p-value and let everyone decide, the reader. So if you do a test, a clinical trial, and you find that you reduce hypertension by 15, but it's not statistically significant, your p-value is 0.06, versus another study that reduced your hypertension by 3 or 4, but you have the less than 0.05. A physician might say, I would take that one that reduces by 15. Why? Because that is our best guess estimate of what it reduces by, because a reduction of 3 does me no or provides no value to me. Okay, so let's keep this. Did I talk about MCID? We're at time, but an MCID is basically a statistically defined number where people will say, I said it earlier, if you give me a reduction of 10, I will consider that as a minimally clinically important difference that would make me change my mind about the therapy. So no, let's not do this. Chat GPT and research. You can use ChatGPT for all your research, including, I'm not saying you should, I'm saying you can. ChatGPT can help you do everything, but you should not use it for everything. Especially, you can use it to inform, but you should not use it to replace, you know. And the more we explore ChatGPT, the more there's discussions about what it can do. I use ChatGPT or AI to do some of the work that I do. I write my abstracts and then I edit it using the AI tools, or I tell it a problem and I say maybe generate a set of codes, then I review, and I review the codes or whatnot. But I don't use it to replace. There are ethical concerns. ChatGPT and AI models could have hallucinate. I actually saw a paper where it makes up values, and when you use your phone, it will tell you, please check Gemini or whatever can be wrong. And so these are the ideas. Use it to enhance productivity. Disclose its use in manuscripts. Don't list it as an author. Do not upload patients' data into your models because they're not owned, and maybe they may not be HIPAA compliant. And use it to augment, not to generate evidence. So we're at the end, and thank you for listening, and thank you for the debate and discussion. I think it was very nuanced, and I'm happy to stay back a few minutes to answer questions, but I think we can stop the recording at this point. All right, I'm going to stop sharing.